talk is about metaphors. Okay, so I'm trying to develop a metaphor for how things are organized and how I think and stuff like that. And one of the things, this is my wife Pam here, one of the things Pam and I do, especially on Sundays, is solve the New York Times crossword. It's not up to British standards in terms of depth of things like the Times Literary Supplement or something. I don't know if that still exists. Anyway, it's a common or garden crossword, and you can solve it. But very often there are things in it that you don't know, and you have to improvise. So I'm going to imagine that physics is a crossword, like this. Actually, on Sundays, it's a 21 by 21, and Pam is an expert at drawing 21 by 21 grids, but we're not going to take the time to do that. But anyway, very often you fill up the crossword, and there are clues in it. And you answer some clues, and then that allows you to interpolate and solve other clues. Okay? So I'm going to put a few clues up here. Actually, I think I need more space. Is there an eraser somewhere? I need a bigger crossword. Very occasionally, the hardest clue is at the top left. Not usually, but this one, some people in the audience may know the answer. Where does, I'll abbreviate this, the number 12 appear in basic GR? Yeah, I'm obviously running out of space. That's just supposed to be the top left thing. If you know the answer to that, I wouldn't be surprised if a couple of people know the answer. And another feature of the crossword that I think I may have to make it a lot bigger. Another feature of the crossword is sometimes down in some other spots, there'll be another clue which refers to a clue that's over there. Okay, so here's the next clue. Where in Mumford does the number 12 appear? Okay, now if you know either of those, you can probably infer how it fits together. And then let's say there's another clue over here. Why is it significant 12 factorizes? Of course, 12 can be factorized in lots of different ways, several anyway, as a product of integers. Why is it significant that it's actually 3 times 4? So there's some clues. Okay, so think about that for a bit. In the meantime, notice in the New York Times crossword, quite often a single square will have a lot of content, not just one letter. Okay, so you're allowed to write whole papers and put them in squares. Okay. So we might ask here, what are the basic Twistor principles? Oh, I forgot to mention something. Originally, I was coming here for the whole month, and I planned 8 lectures, 2 a week. But my department wouldn't let me come. So I think with Magic, we agreed that we'd have 2 lectures, one today and one maybe Friday or something, if it's convenient. But I'm not going to assume that anybody's going to come to the second lecture. So if there is a second lecture, it'll be very impromptu. But actually,
write the answers before the second lecture.
Yes, it's not like some of these series that we've been watching where they keep you hanging. You know, we just finished a whole eight episodes, and it was clear they designed it in such a way there would be another whole season that we have to wait for. Anyway, but what I want to mention is that actually there are 3 lectures. The third one is in this series that you may or may not know, run by a guy called something like Tajunda Singh. I don't know. Anyway, Roger gave one talk earlier, like these are Zoom lectures, okay? So in the third lecture, I'm going to really go out on a limb, okay? So even though today's might be considered ridiculously out on a limb, I'm going to go even further in the third lecture. Okay, then over here in various spots, I have stuff which I'm going to call gifts, whether they are or not. There's Lionel gift there, and there's another one down here. There's one which is relevant to a lot of people in this audience, I think, but I'm going to call it a magic gift because of his stunning work on horizons. The joint paper of him and I don't know how to pronounce the guy's name. Lucietti, is it? Stunning work, and it's in some sense relevant to that. Then because of what Jorg said earlier today, I actually have a Jorg gift. I wasn't anticipating. I was already thinking about talking about something relevant to hypergeometric functions, but Jorg sort of flopped it into my lap, so I thought I might as well go there. It was like purely coincidental. Okay, what else have we got? Oh yeah, there's one more. Whether I'll get to all these, I don't know. This is in honor of the fact that I'm an Irish citizen. What is a quaternion? Okay, that's not, the answer is not as simple as you might seem. And this is relevant because once one answers that, it becomes clear that the question of what is a twistor is equally complicated as the answer to this, or more so, because a twistor is like an octonion rather than a quaternion. And I believe Roger talked about something about that. Last week was so busy I wasn't able to watch any lectures, so I don't know exactly what went on. But he did talk about split octonions, didn't he? Yeah. Okay, so let's get down to business. Now, the other thing about these crosswords in the New York Times on Sunday, it's not on the other days, is that they always have a title, and then they give you a biographical blurb of all of the people who set up the crossword. Here it would take centuries to write the biographical blurb, but there is a title for this crossword. It's called Strange Formulas. Another metaphor for what's going on is what you might call the continuum limit of a crossword, and that's a quilt. A quilt has 2 features. It has now I realize I don't know which is which. There's a warp and a weft. Anybody know which is which? Okay, well, there's a kind of symmetry depending which way you look at it, I guess. So if you do a 90-degree rotation, the warp will turn into a weft and vice versa. Okay, that's probably enough. Let me get down to business here. So what are the basic twistor principles? This actually is a pretty hard part of the of the crossword. So all I'll say is there are at least two features which are critical. Okay. One is the Heisenberg group. The fact that it's critical, I think, actually goes back to Lane Houston. I think was really the first one to really understand its importance. If he's not here, so I don't know if he agrees with that or not, but I would say that that is the key thing. So the Heisenberg group comes up in Twistor theory as a commutator of quantum operators. Well, I guess I should put an H bar in there. The Z's commute with themselves, and the Z bar commute with themselves, and the commutator gives you this. So this is a Heisenberg for 4 degrees of freedom. There are 8 variables altogether. If you think of the Twistor as being 4 complex variables, there's a real imaginary part. Okay, so that's the first thing. But now, if you're familiar with the Heisenberg group, which if everybody's read their Mumford, they should be deeply familiar. I don't know if you have, but Mumford wrote screeds on the Heisenberg group. And a lot of very deep stuff. And in particular, you notice, as he did, of course, that there's a deep connection between the Heisenberg group and theta functions, and everything to do with number theory, stuff like that. But in particular, he noticed, which is pretty obvious when you think about it, that once you have this Lie algebra, in the enveloping algebra, you have four you have a variety of operators. These guys, okay? So these belong to the quadratic enveloping algebra of this thing here. And these form a closed Lie algebra by themselves, okay? So this forms the symplectic algebra. Now there's a bit of notation here. Let's call it SP4. Or do we call it SP4 or SP8? There's 4 X's and 4 P's. I think maybe 8 is probably better. SP4 is usually associated with the SO23, and that's too small. Okay, so we have these operators here which form the symplectic algebra. And then when you start putting together the Heisenberg algebra and the symplectic algebra, you get, in particular, it turns out you have to go to what's called the metaplectic algebra. Which involves basically a double cover of the symplectic part. But anyway, there's a whole sort of structure there which fits together, at least in Mumford's mind, and forms a nice coherent description of all kinds of things to do with number theory, theta functions, etc., etc., etc. By the way, I encourage you to ask questions if you don't understand what's going on here. Or I'll try at least to answer them. Okay. So what are the basic Twistor principles? The problem is that we have both of these. We have the Heisenberg group and, at least in particular, this guy here, which generates the group, actually the way I got it, it's U22. Okay? And U22 is one dimension more than the conformal groups. Basically, apart from a trivial bit, it's basically the conformal group. So it's at some level, the basic Twistor structure is all this. But there's a little bit of tension between the two things. Okay? And it is a question of which one is dominant. And I'll come back to that. Okay? Okay, so why was Lane Houston particularly interested in this? Because, as was mentioned earlier today, he was, although his name wasn't mentioned, he was very much involved in the study of killing spinners with people like Martin Walker and people in the Austin community, relativity community. And it's natural with killing spinners to use them to raise and lower spin. And so then, as was known to Roger also, these operators can be used to raise and lower spin. But I think Lane systematized it. So what's the context in which you systematize? Raise the jigs. Oh, dear. I should have gone to another board. I'm sorry. Well, you just have to remember it. Okay. Where does one see this in action? Well, you can see it in connection with massless particles. Okay. So how do you describe massless particles? Well, there's a well-known way. Let's start with a scalar field. If it's actually a particle, it actually has to have a definite frequency, either positive frequency or negative frequency. So the natural thing to look at is e to the I k dot x over h bar, and then times some form omega k. Okay? So, and what we're looking at here, if it's to be massless, is that Ka is 0. Okay. Well, I'm talking about flat space here. So that's a massless particle. That's a scalar particle. Unfortunately, we are interested in more complicated things than just scalar particles, so we need to improvise a bit to get the other spins. So that leads you to this formula. Now I'll put in indices here. I'm not going to apologize for using Penrose's what I would consider to be standard spinor notation. Times omega k. Okay. So now you have a function that depends on the space-time point, but also two auxiliary spinors. Okay. You might observe this one, of course, obeys the wave equation. Block times 0. Anybody familiar with this? What equation does this obey? Anybody know?
X is a fermionic or...
Oh, no. No room for fermionic variables in this thing. They're forms. They're over here. Well, anyway, it's a routine. Hopefully I'll get the factors right. You take the derivative with respect to x of phi, okay, and you compare that with the derivative with respect to x a prime, and the derivative with respect to x a bar of phi. Then I think you need an I here. There's an h bar somewhere. Is it there? Yeah. Okay. So this is the equation. when you differentiate with respect to x, you pick up a k bar times a k. When you differentiate with respect to each of these x's, you pick a k, one gives you a k bar and the other gives you a k, and there's some factors of I which give you this. What do you notice about this equation? It is clearly a variant of a very standard equation, Schrodinger's equation, right? What is Schrodinger's equation? It's exactly the same sort of thing. Here's a typical Schrodinger type. With an H bar somewhere. Okay. Now this is where Mumford, I believe, made a slight conceptual error. Okay. Mumford writes. I mean, I'm not going to denigrate him at all because he wasn't a physicist, and he probably realized what I'm about to say, but didn't actually write it. So he introduces his theta function, so a typical one, if I've got a formula for it somewhere. Yeah, this is at the beginning. Here's his most basic theta function. It's not actually the one I prefer, but it's that one where you sum over the integers here. He writes an equation analogous to this. There's a 4 pi, I don't remember why there's a 4 pi instead of a 2 pi. H bar has a 2 pi hidden in it. Anyway, he has a 4 pi. D by d. D by dx squared. T. Okay. Basically, so this is when you replace Tor by a real variable. So you can see, just looking at it, these look very, very similar. Okay. So this is theta functions. This is Twistor theta functions. Basically for every formula you write here, there's a corresponding formula in the massless field arena. Okay. Okay, any questions so far? Okay, so what was his conceptual error? Wick rotated. Okay, that's a no-no in Twistor theory, despite the fact that a lot of people work in the Atiyah realm of Twistor theory, where you have positive definite signature, or like Lionel and I did in signature 2-2, where you have completely ultra-hyperbolic signature. Basic Twistor theory says, okay, things are Lorentzian. So the T here should really be real, not purely imaginary. So why didn't he write this for T real? The problem is it doesn't actually converge, okay, when T is real. You need a small imaginary part in T, in Tor, in order that you have decay. But nevertheless, it nevertheless makes complete sense to look at this for T real. It's just that it's not a smooth function, it's a distribution. Okay? Okay. So where is this going? You might ask, what has this got to do with, nobody's asking questions, so I guess I'm going to have to. Oh, sorry. Yes, you're right. Oh, and I interchanged the order of the variables, I'm sorry. Okay. What's this got to do with twistor theory? Is a very good question. And this is where I think probably the work of Andrew Hodges is relevant, although I'm not actually sure that he used this formulas, and I didn't have time to look it up. This is stuff I did centuries ago. What's the omega k here? Okay. Well, that's the key question, or a key question, or might be a key question. It's a function of k and k bar, and then you need to integrate over the k's. So you do a dk a prime dk d prime and a dk bar, and you put two epsilons in. So it's a four form. Okay. So you integrate over this, and as long as what you want, just like in the Mumford case, is you want this to be good when x is real, but even if it's not, you can analytically continue into what's called the future or past tube, depending on your conventions, such that this is definitely convergent as soon as you're in the appropriate tube. Okay. Now, if you read into the very gory details of Mumford, he emphasizes 2 points. One is that you can, as goes back to von Neumann and people like him, there's a unique representation of the Heisenberg group, unitary. Okay? And so basically you can choose whatever representation you want. Okay? So for example, he uses things like e to the minus mod z squared this kind of norm for this is one example, he has several. In this case, there's a ground state, what he calls a ground state, and that's just f of z is 1. Okay. And then once you've got the ground state, you multiply it by z's, and that will give you the higher state. Okay. Well, where is the Heisenberg group in this? Well, it's the Twistor version of the Heisenberg group. So in other words, you have operators z and z bar, which obey the correct commutation relation. So what are they? Z is that, where this means derivative with respect to k bar. I won't write it. And the other one is that. And then they obey the correct commutation relations. Okay? So it's a little bit obscure in this language. So notice in this language, in order to get to a reasonably understandable formula, which I hope this is, you have to sacrifice some of the features of twistor theory. There's no cohomology here or anything like that. Ah, right. I guess it's, let's see. I think it goes probably here. That would be my guess. But there's no I, important fact, there's no I. If you like, take h bar to be 1. So in writing this, and this is something that Andrew Hodges in his wonderful work does a lot, is he doesn't use directly the sheaf cohomology approach, I don't believe. At least not at first, I'm not sure. So here there's no obvious things to do with H1s on twistor space and whatnot. If we do go over to twistor space, what's the analog of Mumford's ground state, well, hopefully people are familiar with this picture. This is a rough picture of twistor space. This is Z bar positive, this is negative, and these are the null twistors. To get an elementary state, you have a co-cycle defined by, I'm talking about the scalar field at the moment, defined by a pair of twistors A and B, and to make sure they have the right frequency, you have to locate the line given by A and B on one side of the twistor space or the other, depending on whether you want positive or negative frequency. So this is your basic ground state. It's often called the elementary state. And then effectively, by moving this around, moving the AB around and taking linear combinations and derivatives and whatnot, you end up with effectively the whole Hilbert space. Although there's a big story about that. But I want to point out in what sense this is actually a quote, vacuum state. Okay? Well, first of all, it's annihilated by these, if I call this psi, it's annihilated by those two operators, because if you multiply by z dot A, you eliminate this pole. If you multiply by z dot B, you eliminate that pole, and so the answer is just then 0, because you need two poles to do a decent contour integral. Okay? What else is it annihilated by? Well, if you think about it a bit, it's annihilated by c dot dz and d dot dz, like that. What are C and D? Well, they are two planes that go through that line. Okay? So in actual fact, there are four operators that annihilate it, and this is in accordance with general principles of quantum mechanics. For example, if you have x's and p's, you can use functions of x, which eliminate half the degrees of freedom. Here, you're eliminating half the z degrees of freedom, half the z bar degrees of freedom. Think of d by dz as representing z bar. This therefore qualifies as some sort of ground state, if you like. Okay, now I'm going to make a fairly dramatic, two dramatic extrapolations. Okay.
You might use the other four.
Oh, good idea. I need to get to those gifts also. So somebody remind me if I get too carried away.
You're halfway there.
Halfway through the talk, is that what you say? Okay. No, I certainly want to get to it. Okay, so I'm going to make two very big jumps at this point. Yep.
I mean, is that function that that was for genus 1 or something, or it was just for one fixed genus? What is that?
It's the most. I'm not very much of an expert on Riemann.
Usually you have a Riemann matrix of G by G or something.
Okay, so this belongs to the basic family where you have four. Riemann had lots of quartic relations amongst the thetas. It's those ones. They often, Mumford calls them theta half half, theta minus a half half, and so forth. There's four of them, and all kinds of incredible identities developed by Riemann. I think it's genus 1.
I would think it's genus 1.
Yeah, I think so. But don't quote me on that. Excuse me. Where was I? Oh yeah, I'm going to make some conceptual jumps. So the first one is this. This is not really a big deal, at least in some sense. Okay. Here you just put in and then the rest of it is unchanged. I'll abbreviate this thing as D2K bar D2K. Okay? So what have I done here? I've replaced what was a quadratic in K by essentially an arbitrary function in K, up to some rules. Okay? So notice what's happened. We've jumped from a four-dimensional space-time to an infinite-dimensional space-time in one move. Okay? So that's one of the metaphors of this talk. Okay? Whether it's good for anything, I'm not sure. So here your field now depends on your choice of function. Okay? If it's just a quadratic function like this, then you get it.
Sorry, that's an S of kappa and kappa bar.
Yes, it's a function. You're integrating over the kappa. So this is a function of kappa and kappa bar. So you think of the space-time coordinates as being, expand this out as like a Taylor series. Okay? And the space-time coordinates are the coefficients of that Taylor series. So you've got linear ones, quadratic ones, and cubic ones, and so forth, going on forever.
What happens to these numbers XA?
Oh, well, they're coefficients. That's a case where X looks like, well, this would be S. Yep. That would be S. So they're just coefficients. So it's like, so it's an infinite dimensional generalization of the spin button. Okay? Okay.
So this could replace global holomorphic curves by local holomorphic curves.
Might well. Yeah, I'm not going to give a geometrical interpretation, but that could well be it. Okay, I'll come back to something like that in a minute. Okay, so this is old stuff. The new thing, I should have mentioned at the beginning of this talk that my talk is chaotic because things have been completely turned over in the last few weeks. Things have occurred to me that had not occurred to me before. I left out an important, wow. My co-worker is Jonathan Holland. And everything I say, at least the correct stuff, is due to him and me. Anything that's incorrect is due to me. Okay? We've worked together for a long time, and we've been developing all kinds of things, which I'll hopefully come to. And anyway, let's get back to this. So everything I'm talking about is due to me and Jonathan Holland. Where was I? Yeah. So this to me is routine, okay? The next step is definitely not routine and possibly controversial, okay? So imagine that you are, in fact, interested in massless particles. The question is, what are they and what are they for? Okay? Well, when you look at the universe, you're actually using massless particles all the time, right? When you look at a star, you see the star. So what's happened? Information about the universe is being transferred from the star to you. Okay? Therefore, massless particles are about transfer of information. So the question is, what is the information? Well, look at this formula here. It looks sort of haywire. Okay? You've got this enormous thing here, and just some little function here, sort of, this is the thing that is giving you the input that tells you which wave you've got, okay? But it seems lopsided. So the question is, how do you make it unlopsided? Well, here's the answer. You put it holomorphic on this side and anti-holomorphic on this side. Okay? So in other words, I've imagined splitting this as a tensor product of holomorphic bits and anti-holomorphic bits. At this point, you might object very strongly that this is haywire, okay? I'm not sure whether it is or not, but I thought it was worth talking about.
So usually when we think of the function
That's this guy.
Yeah, so that's a function, roughly speaking, on not just the micro-dimension space, but also the circle one above it.
Yes, I forgot to mention, I forgot a key thing about this formula is that you're integrating over 4 Ks, not 3. If in the original, if you fix the spin, you can get by with 3 Ks.
So it contains all possible spins.
Yes, that was the whole point.
Yeah. And then but now down there, instead of going from a function of 4 variables, you're going down to a pair of functions of 2 variables, aren't you?
Well, one complex conjugate of the other. So I'm thinking of it as...
It's a function of 2 variables.
It is at the moment. That's a clear objection. How can we get around that? Well, first of all, what kind of functions are we talking about? This is the key feature. I'm thinking that these are entire. Okay? And similarly for the other one. Okay? But what functions do we put here? Well, if you look at this, it doesn't seem quite right. And what you should, in fact, put is so these z's are the z's that I have up here. They're the k's and the d by dk. So the derivatives will act on this thing here. Okay, one will act from the left and the other from the right. Okay, notice if this is correct, which honestly I only give it like 20% or so, but definitely non-zero. If it's correct, then it violates the basic assumptions of von Neumann in quantum mechanics. In quantum mechanics, these spaces have to form a Hilbert space, and they don't. Okay, they form what's called a Frechet space. But notice the amplitude is in principle completely well defined. So you have input space, which is a Frechet space, output space, which is a Frechet space, and this interpolates between the two. Okay. Okay. So that's one controversial thing.
But you might just make it into a Hilbert space for some.
Oh, yeah.
Exponentially decreasing the measure.
Yes, but you can't do it naturally. It has to be invariant under SU22 or under appropriate things. I don't think there's any way to do it invariant.
I see.
I believe. I could be wrong.
15 minutes,
okay, let me get to the next controversial thing, which is associated with the gift to Jorg. I meant to do Lionel's and Maciek's first, but the way things have evolved. So Jorg mentioned hypergeometric functions. Well, it turns out that these occur naturally in connection with spin networks. I don't know if people are familiar with spin networks. You have states which are labeled by spin, 5, 4. I'll probably do something wrong here. So you have input spins, some sort of mediator, and output spins, and they have to obey various rules, triangle inequalities and stuff. In particular, if you do this kind of thing, you end up with a hypergeometric function. But how? Well, actually, this was treated in my thesis, and at the time, I just dismissed it as being just trivial, okay? You know, Roger had this lovely theory of spin networks, and I figured out, okay, I can do this. What I wanted was a theory that was, this is one of the key metaphors here, theory that didn't depend on the particular parameters. Like in the previous example of massless particles, I didn't have to fix the spin, okay? I wanted to have something that's universal for all spins at once. Similarly with spin networks, okay? So what kind of things do you do here? Well, there's a very famous one. there's a famous concept that I'm sure Jörg, having read Klein, will have seen. And I forget, is there a umlaut over the O? No? Or over the A or something? No? A Pock hammer contour. Okay? Pock hammer contour is you have two things which are not poles. I mean, they might be poles, but then you go around. Am I going to get this right? Hopefully, that's correct in one way or other. Okay, that's a Pock hammer contour. So you notice if you remove the poles, it shrinks to nothing. Okay. Okay. So what's the most fundamental example of the Pock hammer contour? This is where I'm going to get really controversial. It's where you have three poles. So how do you write the amplitudes? How do you write these amplitudes? I'll do it projectively. I could probably do it non-projectively, but I won't. So you have pi d pi, which is your basically dz kind of integral, and these are just linear functions of, Jörg alluded to them, pi dot alpha, pi dot beta, pi dot gamma, sorry, my writing's bad, raised to some powers, okay? And the important point is that a, b's, and c's do not have to be integers as they are in the spin network, standard spin network theory. I never made a big deal about it, but I'm thinking that maybe there is a big deal to be made. And what's the contour here? Well, you've got three poles, like that, and what you do is you loop around like that. So unlike the sort of basic Pock hammer, which just uses two poles, here it's natural to move, this is equivalent to this by distorting the thing around the Newton sphere. So you get this. Anybody know what the answer is? No, hypergeometric, I already mentioned, is 4. We'll come back to that. It's simpler than yes, it's the beta function. So this gives you what's called the beta function, and this gives you string theory. By the way, one of my teachers that I mentioned, Jeffrey Goldstone, was one of the key things in proving 26 dimensions for bosonic strings. I think he was the major player. Don't quote me on that. Okay. So what am I going to say that's controversial? I'm going to say that string theory is spin network theory. Okay? That they're dual in some abstract sense. In the sense of what's called the Langlands conjecture. It doesn't look like I'm going to get to the solid part of my talk. The thing about this is it is actually a generalization of spin network. Spin network is based on SU2, but these spinners here could be based on other groups like SO12. And so you're talking about hyperbolic spin networks instead of the traditional Penrose spin network. I never really sort of grasped that that was an important thing in the past. Okay? So I'm thinking that there's a duality between string theory and spin network theory. Okay? Okay, so where does that leave us? In terms of the quilt, string theory is the warp or the weft, but not both. Okay? So I'm claiming that string theory is incomplete. And if you take anything that I say seriously, you have to go beyond that. And beyond that will get you automatically to twistor theory. Okay. So Jörg's gift. The hypergeometrics here are basically the same thing. Oh, I forgot to mention there's the whole thing is homogeneous here, so A plus B plus C. They're complex numbers, but they add to -1. Okay. hypergeometric's basically the same, except you have, I'm pretty sure this is in my thesis, I'm not sure. It certainly was around at that time. Let's say A plus 1, B plus 1, C plus 1, and D plus 1. And then the sum of these guys has to be minus 2. And now you have 4 poles. To do an integral, you have to make sure that you go around in such ways to come back on the same sheet. And that means you have to do a Pock hammer contour. So there's various Pock hammer contours you can do depending on which pole you leave out. Okay? And that gives you a variety of hypergeometrics that Jorg was talking about. If you think of it in terms of SL2, you can think of this as being transformed to basically 0, this to 1, this to infinity, and then this is somewhere. And so ultimately, it's just a function of z, which is the standard hypergeometric thing. Okay? So my gift to you is that somehow this might be relevant to something in your work. The point being that you can make these parameters arbitrary, and maybe you can sum things with coefficients and get some macho formula, which has got lots of these things put together. Okay?
Is there some kind of cosine symmetry? Is there some kind of cosine symmetry which relates different contours?
Yes, there is. It's very standard stuff. Yes. Okay, what about the next gift? Maybe I'll go, I'll save Lionel's for a moment. I'll go to the one for Maciek. Okay, so in this recent work of Maciek and Luccietti, they do what's called, I think, honestly, I'm not an expert on this, near horizon theory. Is that, would that be a fair statement? Okay. As far as I can tell from the paper, it's not conformally invariant. Is that right? Okay. So what I want is a near Scry theory. Okay? But not in 4 dimensions, in arbitrary dimensions. So in other words, repeat the whole theory that you have here for horizons, but for Scry. Now, in some sense, I should have done this myself a century ago in collaboration with people that hired me in Pittsburgh, in particular Paul and Ted Newman and all those people. They were experts on this stuff. But that was before the application I have in mind was available. Okay. So what we want to do is redo the Scry theory into a near Scry theory. But you have to allow, unlike I think in Maciek's work, you've got to allow for more general signatures. Okay? So why do I need this? Well, as I mentioned, there's a fundamental dichotomy in twistor theory between the Heisenberg aspect and the SU22 aspect. Where does the SU22 aspect crop up? Well, it crops up in this. So what am I thinking of here? I'm thinking of a space-time, 4 dimensions here. I'm looking at the local twistor connection, which is also equivalent to the Cartan conformal connection. I have a feeling this is going to be talked about tomorrow a little bit. Anyway, you write down this tensor, okay? So it's a tensor, a local twistor tensor. And if you write it out in gory detail, what you find is that the skew part, this is just basically the canonical 1 form. 2 form, sorry. Symplectic form. Except it's not symplectic because we're working with null twistors. So you might think of it as a degenerate symplectic form. Okay, but it's the symmetric part that's key. Okay, this gives you the Pfefferman conformal structure of any hypersurface in space-time. Okay? Out of time already? 5 minutes, okay. This is the Pfefferman conformal structure, and that means it controls the entire Twistor structure. In fact, curved Twistor theory, you could argue, is nothing more than this tensor. Okay? Everything follows from this tensor. But notice that this works in curved spacetime. This is defined in an arbitrary spacetime. But it's degenerate because it's killed by the null geodesic spread, which I would normally write something like this. If I take the symmetric, let's do the symmetric part here. Let's call this F of Pfefferman. It's killed by the null geodesic spread. So in the analogy with Scry, those are the generators of Scry. Okay. Now once it's killed by that, it's now non-degenerate, but even then it's not conformally invariant. What am I trying to say? No, that's the wrong statement. What am I saying? Oh, sorry. There's an additional. Yeah. Sorry. It's killed by this, but it's also killed by. I mean, these things are easy to check. If you dot that with F, this should be a dot here. That's here. So this is real scalings of the spinner, and this is the null geodesic spread. This is the problematic one here. This is kind of trivial. This just means that when you quotient out by this, you don't have a metric per se, but a conformal structure. So what we have is a conformal structure which is degenerate in one direction, and that's the idea that there is in Scry. So the question is, if you take that conformal structure, is there, and it would have to be somewhat canonical, is there a canonical neo-Scry theory that goes with it? I mean, this has certainly occurred to me in the past, but it's become more pressing given the work of Luccietti. Okay.
There's a nice kind of structure on the asymptotic Twistor space.
Yes, I was surprised you didn't mention it. That was constructed by Ted Newman, Paul, and at least one other author, wasn't it?
I thought it was Co something.
I think it was a joint paper of a bunch of people, none of whom was me, even though I was there. As you say, there is a very nice Kähler structure. It's precisely this. That's what it is.
Yeah, of course.
Okay. Pseudo-scalar.
Yeah,
Pseudo-Kähler, I should say.
Yeah, and you can write that down very explicitly in terms of the asymptotic.
Yes. Okay, so I've got a couple of minutes to say a couple of things about that. If somebody wants to ask me about the 12, I'll get back to that. But I want to do Lionel's stuff. Where is it?
I think one of them is break but it's too hard. I can take one of them is break if it's too hard.
No, I'll finish quickly. So here's one way of writing the Twistor structure on Scry. Lionel alluded to it yesterday, where the shear goes here, okay? And in this language, the shear is a function of degree 1 and minus 3 think of it as in Z and Z bar. Where Z bar is just basically the pi bar. What's that about? Is that telling me I have to finish? Oh no, it's some. Is there any way of getting rid of it? Don't answer it. We'll know what happened. I never answer the phone. Basic rule. Yeah, it's my phone. Anyway, this is this. So typically, you think of this as a function of u, zeta, and zeta bar, where these are the pi's. Okay? But suppose you write down this and say, okay, I want it to be a complex structure. You do not get this. What you get is, if I've done it right, you get that. The integrability conditions for this to be a complex structure. Okay? This is not saying that sigma is a function of u. What would it take to be saying that sigma is a function of u? You would need the other. This formula would have to be true. Basically because you're looking at things like x dot pi bar being u, and it's symmetrical between prime spinors and unprime spinors. Okay? So this is something I noticed about 40 years ago, maybe. That there's a potential for a slight generalization of what you mean by Scry, or the shear function in where you have this equation rather than just a SU. And it seemed like stuff Lionel was saying is somehow possibly related to that. I'm not sure. Okay, 1 minute to give your other present. The other present is you wrote down a lovely action yesterday, which was for gravity, right? So what I'm saying is take your D3Z thing and put a 4 there, and change all the homogeneities so that you have arbitrary homogeneity rather than specific ones as you had. And then you'll get a new theory which includes what you were talking about as a special case. Yes. Okay. Okay. Now I didn't get to the 12. Does anybody know about the 12?
Yes.
Okay. And then we can quit. Okay. 12. Where does it come from? Well. You're on the right track. Weierstrass P function. Hopefully you remember it. Hopefully I will. That's a Weierstrass P function. Okay? If you differentiate it, the only calculation I've done today, I guess. Hopefully we'll get it right. Looks right. I'm teaching a calculus class, so I'd better get it right. Looks right, doesn't it? Now we have a p prime which we can get rid of. Okay. Now we differentiate again. Okay. Well-known calculation is that you can divide by 2, as long as we're not in characteristic 2, and you get that formula. So that's the 12. Okay. Why is that relevant? Anybody know? In general relativity. I'm sure it's well known. I just don't know where to find it in the references. Okay? What you look at, first of all, where do these Weierstrass functions come from in general relativity? Everybody knows that, presumably. Null GD6 of Schwarzschild, right? Or Kerr-Newman, or the one with the one that we had today with Q squared and lambda. All those ones can fit into this umbrella. So when you study the null GD6 of Schwarzschild, you end up dealing with the Weierstrass P function. Okay, so where does this differential equation come from? Well, it comes from the GD-Zik deviation equation. Okay, you study the GD-Zik deviation equation. I'm only talking about null.
Can't you solve those without P functions?
No, you need the P functions. There's constants of integration. If you put some constant 0, you can certainly find some solutions without using Twistor. But anyway, it actually comes up in geodesic deviation. So what is the geodesic deviation equation? Okay, it ends up being L double prime. I'm not sure if I'm going to get the sign right. I think it's right. It's that equation. Okay. Does that ring any bells? I'm supposed to get to the Sachs equation, which is partially integrating this and then reducing it to first order, and then relating this all to plane waves in general theory of plane waves, but I haven't got time, obviously. So this is another famous equation. Anybody know this one? Haven't read your ints. It's in the library. Well, 12 factors is 3 times 4, as I mentioned earlier. Right? Does that ring any bells? No? You're all going to fail your 1890 tripos exams in math. It's that equation. Anybody ring any bells here? This is what's called the Lamy equation. So the geodesic deviation for Schwarzschild is none other than the Lamy equation. But it's not just any old one. It's the one with n is 3. Okay. Now, Jonathan and I really stewed over whether it was 3 or 6 or 24, or we're absolutely confident it's 3. And I'm sure it's in the literature somewhere, but I don't know where to find it. Okay? So why is this one special? Because you can solve it using this fact. Okay? If you think about it a bit, it's obvious. Oh, it is obvious, isn't it? You just put P here, and then this is P triple prime, and this is, sorry, P prime. You put L as P prime, and you obviously get, this obviously converts into solution that. Now that's an absolute miracle. It happens with n is 3, and not any other value of n. In the other values of n, you end up with a denominator which is a polynomial in P, and up here, G prime of P plus a constant. Okay? So I claim that without proof, because I've only checked it up to n is 10 or something, that you can solve the Lamy equation for n here. It's probably an int, so I wasn't quite clear. You can solve the Lamy equation for n with a polynomial here of degree n. Okay? And only in the case n is 3 does it match this cubic here. Okay? When n is 3, this GP is that one. And that gives you this formula and this formula here. Okay? If somebody has a nice proof, and I think it's probably an int, that this is actually always true for arbitrary integer n. All these equations go haywire if n is not an integer. Okay? And why is it important that n is 3? Because this also gives you, as Mumford remarked, this gives you a stationary solution of the KdV equations, and it has what's called a spectral gap. And because n is an integer, there's a spectral gap. And there's a whole theory of integral systems which uses those spectral gaps. And so the final thing is to bring it back to Lionel, and then I'll quit, one more sentence. Lionel and I wrote a paper on solitons, and in it we introduced well, actually we wrote 2 papers on solitons, but one of them on the soliton hierarchy, okay? In writing that paper, we came up with this thing called the Bogomolny hierarchy and wrote it down. We only had a trivial application of it for SU2 or SL2C or something. It involves arbitrary matrices of arbitrary size, in principle infinite, but we only had a trivial application. Well, I'm claiming that, not quite with proof yet, but almost certainly, that underlying the theory of plane wave spacetimes is this Bogomolny hierarchy of line 1 and I. And so, in other words, we solved the problem of where to find Twistor-like structures inside space-time. What you have to do is do it for each null geodesic and then see how it patches together as you form the null codes.
Thanks for the great talk.